ado, introduce Dr. Tom Hatta.
Welcome everyone. Thank you for being here. My name is Tom, and today we're going to talk about protein screening and intrinsic viscosity measurements with the VROC initium. And so today I want to go over first an introduction of our core VROC technology and how it's implemented in our VROC initium, our automated viscometer, as well as the concept of Viscosity Fingerprinting, which is made possible by this technology, which is basically the thorough characterization of viscosity under any number of physical parameters to map out in great detail the rheological properties of your products. And along those lines, I'm going to introduce a few applications such as the injectability of your proteins, as well as concentration screening, and finally some intrinsic viscosity measurements of your protein solutions. So to start off briefly, what is viscosity? Well, viscosity is the fluid's resistance to flow, essentially. And so when you're pushing on two tubes such as this, one filled with a low viscosity fluid like water and one with high viscosity, it's going to take a lot more force to push that high viscosity fluid through if you're trying to push it at the same speed. So in other words, viscosity, otherwise defined as shear stress over shear rate, or meaning your force or how hard you need to push versus how fast you're causing the fluid to flow. And the technology behind this is a VROC, which is our Viscometer Rheometer-on-a-Chip. And VROC is a hybrid of microfluidic and MEMS technologies. So you have a microfluidic glass chamber with a silicon membrane, and on the silicon membrane you have 4 MEMS pressure sensors attached. And by measuring the pressure drop across these sensors as you flow a fluid through, you are able to calculate viscosity. And so the features of the VROC are that it can measure absolute viscosity because we can control the shear rate or the flow rate. Small sample volume, we can measure as small as 12 microliters of fluid through this chamber. A wide dynamic range in shear rates. And because it's a flow-through system, it's inherently high throughput because it's easy to clean. Once you push your sample through and you take your measurements, you're able to push your solvents through to clean it and then dry it, and then it's ready to go again. And because of the precise nature of this technology, it also offers superior repeatability, about 0.5% of reading. And so here's how this technology works. When you push fluid through the chamber and across the pressure sensor array, you can see a linear pressure drop develop. And this pressure drop it correlates with the shear stress. And your flow rate correlates with the shear rate. And when you divide shear stress by shear rate, you have your dynamic viscosity. And so this VROC chip is implemented in our VROC initium. And the key features of this product is that it is a high throughput automatic viscometer and rheometer, meaning once you load your samples and set up your job, you can let this run overnight unattended. And currently it can measure samples as small as 26 microliters loaded into a vial. We are always constantly developing this product, and we're pushing to make the minimum sample volume even lower. And you can load these samples either on a 40 vial rack or a 96 well plate. And this product also offers sample retrieval, which means that once you measure a sample in the chip, then the syringe pump is able to retrieve that same sample, and you can take another set of measurements theoretically indefinitely, and so you can either set the same shear rate and temperature, or you can adjust those so that you can actually have a shear rate and temperature sweep of a single sample. And with built-in Peltier temperature control, you can measure between 4 and 70 degrees C, and independently of that, you can control the temperature of the sample tray between 4 and 40 degrees C, and this is where your samples are sit while they await measurement. And what this product unlocks is the process of viscosity fingerprinting, which I mentioned a little bit earlier, and this is the thorough characterization of viscosity under any number of physical parameters to really map out the detailed rheological properties of your products. So anything from concentration effect to pH, buffer, excipient, temperature and shear, denaturants, and any other physical parameter that you can think of that would manifest in a difference in viscosity. And some of these key applications for these detailed measurements is looking at the injectability of a candidate protein, the molecular size in formulation, as well as the stability of your protein or polymer in formulation, as well as the kinetics of chemical reaction and degradation, meaning how does the viscosity change through time as you're looking at certain reactions. And so I'm going to cover our first example application, which is injectability. I left a couple of links here on from our website if you want to look into this further. And so when looking at the injectability of a candidate protein, there is a trade-off in that an increase in concentration of your candidate drug usually corresponds with an increase in viscosity. And the problem with having too low of a concentration means that you need larger or more frequent dosages, so it's not quite efficient. But at high viscosities, the drugs are either difficult or impossible to inject. And usually the standard cutoff for this is about 50 centipois, and it can be lower. Sometimes the standard is as low as 30. And not only do you need to know how viscous your sample is at a given concentration, it is also important to know how sensitive it is to changes in concentration. So if you look at the points in red, very small concentration differences push up the viscosity to above the centipois level, which suggests that you need to be able to account for this variability in concentration that can come about due to even mild degrees of evaporation. So it is really important to characterize these viscosity concentration curves in detail when looking at, say, your candidate drug. And following that application is also the ability of concentration screening. So this is actually where we generate some of these viscosity concentration curves in our lab to showcase the abilities of our product, the VROC initium. And so what we did was we fingerprinted the viscosities of 6 samples of glycerol water solutions at 3 different temperatures. And so these samples range from 0% to about 90% glycerol. And we measured at 3 different temperatures, 20 to 30 degrees C. So each sample was measured at 3 temperatures. And we did 10 measurements at each of those 3 temperatures per sample. And so that means we were able to make 180 unattended measurements because we set these samples on the tray, we set up the job, and then we went home and the data was there when we came back in the morning. And so here are our measurements. And what you can see is it actually covers 2 orders of magnitude of viscosity measured in a single setup. So we measured from about 1 centipoise or millipascal seconds to about 100, and shown by the dots. And the dashed line shows the curves of the reference standard. And so you can see that for every concentration at every temperature, we have very good agreement with reference values. And we were able to do this with not much sample at all. So some of our samples were 100 microliters loaded, and some of our samples were about 26 microliters loaded. And third is intrinsic viscosity. And so this is because it is an amazingly powerful tool. We spend a lot more time visiting intrinsic viscosity. And so intrinsic viscosity is a measure of a solid's contribution to viscosity in a given solution. And it's used frequently in polymer science to calculate molecular weight, and it can also be used to measure the hydrodynamic radius or the hydrodynamic volume of your solute in solution. And it can also be used to measure stability as you change your buffer type. For example, adding a denaturant will usually lead to an increase in intrinsic viscosity as your polymer denatures and essentially opens up in solution. And it is useful for screening candidate proteins in early stages of development, as you're able to characterize important solvent properties. And it also is a great complement to other techniques used to measure hydrodynamic radius, such as dynamic light scattering, or DLS, because it can work in situations where DLS data are difficult to interpret, and such as when you are working in a complex medium. So what is intrinsic viscosity? Again, we're measuring the solute's contribution to viscosity, and so how it's typically done is you add little by little of your solute to your solvent, and you look at the corresponding increase in viscosity. And so here is the definition of intrinsic viscosity, and what we are measuring is actually the specific viscosity, so the viscosity of your solution at a given concentration minus the viscosity of the solvent divided by the viscosity of the solvent in order to figure out that contribution of the solute, and you sort of normalize that by the concentration, so specific viscosity divided by concentration. And what you want to know is that value as the limit of, as the concentration goes to zero. That's because as you increase the concentration of your solute within the solution, you start to see more and more actually the effects of the solutes interacting with each other. And so what you want to know essentially is what is the contribution of a single molecule of solute within that solution. And one thing to note is that as you increase the molecular size of your solute, you often see an increase in this effect. So you would expect to see a higher intrinsic viscosity for particles in blue, such as this, versus the particles in red. And an important thing to note, again, is that the viscosities must be measured at low concentrations of solute due to the interactions of the solutes with each other at higher concentration, because what we want to know is how the solute and the solvent are interacting. So here are some measurements that we've made in the lab, and we made solutions of bovine serum albumin, or BSA, and bovine immunogammaglobulin, or IgG, in PBS. And to make these measurements, we made 100 microliter samples drawn from dilutions of a stock solution. So we made stock solutions about 50 milligrams per milliliter, and we diluted those down to about 40, 30, 20, 10, and 5 milligrams per milliliter. And for each of these samples, we took 20 measurements using the VROC initium's feature of sample retrieval. And so having a large number of measurements allowed us to screen for data quality, because we were able to look at those runs that gave us perfectly good steady state pressure data in order to calculate an accurate viscosity, and we were able to throw out outliers. And so the resulting repeatability of those measurements was within 0.5% of all samples. So what you can see here are there are very tiny error bars on this graph, and I actually had to increase the error bars to 3 standard deviations in order to have them be even visible on this graph. And the high repeatability of the VROC initium is absolutely needed to detect these minute differences in viscosities, because when we are looking at differences in concentration of about 5 milligrams per milliliter, this corresponds to about the difference in viscosity of about 0.02 millipascal seconds, so incredibly small differences in viscosities. So you need that sort of repeatability in order to accurately differentiate small differences in viscosity. And so once you have your viscosity measurements, you actually convert viscosity to specific viscosity and divide that by concentration. And so what we have on the x-axis is still concentration. On the y-axis we have specific viscosity divided by concentration. And what we're curious to know is the limit as concentration goes to 0. So you're trying to find the y-intercept of this line, and that value is your intrinsic viscosity. And so this is the Huggins method of calculating intrinsic viscosities. There are several other methods as well, and so one is the Kramer method. So instead of specific viscosity, we're using a natural log here, but the values, or the y-axis value, should converge on the same intrinsic viscosity, and so oftentimes these methods are used together, and the average is used to get one valid value. And so we analyze our IGG data for agreement of intrinsic viscosity between the Huggins and Kramer methods, and roughly we have a value right here, and we also did this analysis with BSA, and we came with another intrinsic viscosity measurement for BSA, and what you can see here is IGG. The intrinsic viscosity is significantly higher than BSA, and again, going back a few slides, I mentioned that for molecules that have a higher molecular size, you're going to expect to have a higher intrinsic viscosity value. And so what we see here is IgG, yes, it is a larger molecule than BSA, and so those intrinsic viscosity measurements are in line with what we observe looking at the molecular weight of these proteins. And because we know the molecular weights of those proteins, we don't need to calculate that, but we can, however, use intrinsic viscosity to calculate molecular weight, and if you don't know that value, and that's extremely important in polymer science when you're actually looking at molecules that can have a variable molecular weight. And so you would use the Markowitz-Sakurada equation displayed here, and the two coefficients K and A are sort of empirically derived, and so it's important to note that they are dependent on the polymer conformation in the solvent. So it is highly dependent on the solute-solvent interaction. And going a bit further, you can also use molecular weight and intrinsic viscosity to calculate your hydrodynamic radius. And so one example is using the Einstein-Sima equation. So in summary, viscosity fingerprinting is a powerful process with many applications, such as injectability and intrinsic viscosity. The VROC initium is an ideal tool for this technique because of its high accuracy and repeatability. It's used for small sample volumes, so especially in environments where each sample is incredibly precious, we can use a very small amount of sample volume, and sample retrieval means that you can take multiple measurements with the same sample, and that all of this can be run unattended, which lends itself to a high throughput process. Again, this is the RheoSense team. I'm Tom Hata. We will be happy to answer any of your questions. Feel free to contact us. And thank you.